Yeah, it's now started. Yeah. So in the last theory class, we saw how to uh, solve a Boolean expression using Boolean algebra, and then we came over to talking about a Carnot map. What is a Carnot map, and why do we need to use it? What is its advantage vis-a-vis Boolean algebraic methods, and what are its disadvantage? Okay, what is the major disadvantage? Why we cannot always go in for Carnot maps? What is the case where we have to use Boolean algebraic techniques to to optimize the Boolean expressions? Okay, today we will be taking our understanding a bit further by first talking about the standard terms, that is the sum of product and product of sum terms. Then we will talk about the canonical terms. Canonical terms are the sum of min terms and the product of max terms forms. And then we will see how to actually represent the values in a Carnot map and how to use this pictorial diagrammatic technique to arrive at a final optimized Boolean expression. Okay, bete? Is this clear? Are we in line with each other?
Yes, ma'am.
Yes, ma'am.
Right. Okay. So I'll start my presentation, right? Kashish, can you please put the message on the WhatsApp group that if some people have left the meeting, they can rejoin. Okay. I'm starting the presentation, however. Okay, so if you remember last time, we had talked about what is a min term. You remember that?
Yes, ma'am. SOP.
Yes. First, we had said that all these terms, when written in this format, actually represent the min terms. So for every input combination in the truth table, there is a corresponding min term, right? So we had said that for n Boolean variables, there will be 2 raised to the power of n min terms. Now, what is a min term? How is it different from a normal product term? The difference between a normal product term and a min term is that in a min term, all the literals, for instance, if I have a Boolean expression f, that is a 3 Boolean variable expression, then all the literals A, B, and C must appear in every min term. They may appear in a complemented form or they might appear in a uncomplemented form, but they have to appear. Okay, so that is a min term. As contrast to this, a product term is a simply ANDed term, logically ANDed term of any two literals, and there is no necessity that all the literals present in the Boolean function must be present in the product term. Is this clear?
Yes,
Yes,
ma'am.
ma'am.
Accordingly, we had talked about two notations, namely the sum of product form and the sum of min terms form. Okay, so how to represent a Boolean expression, let's say f abc is equal to a dash bc or a b dash c dash, this expression that you're seeing on your screen alternately. So this sigma is used to represent the sum of min terms form. It is used to represent the sum of min terms form. Now, sometimes, although we have seen this precise difference between the sum of min terms and sum of products form, but still Sometimes, in common language, sigma is used to denote it is said to denote a sum of product form. Why? Because actually, if we see, sum of min terms form is also a sum of product forms with an added restriction that in each term we must have all the literals. Yes or no?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
So, in common language, sometimes in some books, you may find that people say that sigma is used to represent the sum. You already know from your mathematical background, maybe even if you had maths till 9th or 10th, you will know that sigma is used to represent sum terms, sum of something, right? So, sum of products. Now, sum of products, which products? So you can see sum of, as in this case, for example, it represents sum of minterms 3, minterm 4, minterm 5, minterm 6 and minterm 7, which you can verify from this table. Is this clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Right? So this is an alternate representation for the uh, SOP form. Okay. Now, let us introduce ourselves to what is a max term. Okay. Now, please see, a max term in contrast to a min term is an odd sum of literals. Okay. What was a min term? It was an ANDed sum of literals. Okay. In which each variable appears exactly once. That means the restriction still stays, the same restriction that was there in a min term, that every literal has to appear, okay, in the term in either true or complemented form. So it has to appear once. And obviously, since it will appear once, it will either be, for example, if it is a Boolean variable A, then it will either appear as A or it will appear as A dash, because both of them cannot appear together. Okay, because in min term, if both of them appeared together, A dash, it would have made the entire min term is equal to
0.
0.
0. And here it will make the entire max term is equal to
1.
1.
1.
1.
Okay. I may keep on ORing as many number of literals as I want to this max term. Then if I put A or A dash and then I add to it or B dash or C dash or whatever, it will eventually come out to be 1, because
Yes, ma'am.
A
Yes,
or A
ma'am.
dash is 1, and then 1 odd with anything always gives me a 1.
1.
Okay, so that is why you see but not both condition augmented here. Okay, this also holds for the min term. Is this clear?
Yes,
Yes, ma'am.
ma'am.
Yes, ma'am.
Yes, ma'am.
So the only difference between the min term and the max term is that min term is a ANDed sum of literals, and here this is the odd sum of literals. Okay, now how to obtain the max term form? In the min term, we looked for a 1. Okay, here we are going to look for a 0. So find the truth table rows where f is 0. Okay, every 0 in the input column implies a true literal, and 1 in the input column implies a complemented literal. Let us see what this means. So this is the same truth table as before. If you can see, right, the truth table of 3 Boolean variables. Now you remember, for what was the min term for x is equal to 0, y is equal to 0, z is equal to 0? It was x dash, y dash, z dash. Is this clear?
Yes, ma'am.
Yes,
Are we
ma'am.
on the same page? Yes. This is what
Yes,
we have
ma'am.
already done. Yes. Now, what would be the corresponding max term? Please see, we have said in the definition itself that Instead of the and, what will appear? Or. What will appear? Or.
Or.
Right? And you just saw how to find out a max term from the truth table. So in the min term, x is equal to 0 implied x dash, whereas in a max term, x is equal to 0 will imply a x. Okay, and x is equal to 1 will imply a x dash. And this is true for all Boolean variables which are a part of the max term. Okay, so it is opposite to the min term. It is opposite to the min term. So what will be the max term corresponding to the first input combination? It would be x or y or z.
Z.
Is this clear?
Yes, ma'am.
Let us look at the second term now. It will be x or y or z complement. Is that clear?
Yes, ma'am.
Yes, ma'am.
Okay, speak up the third max term for me, please.
X or Y complement or Z.
Complement or Z.
Excellent. Next one, please.
X complement
X
or
or
Y or Z.
Z.
Very good. So now let us see another thing. Obviously, as was the case with the min terms, the number of max terms will also be 2 raised to the power of n if we have n number of Boolean variables. This is clear?
Yes, ma'am.
Now, the next thing that I want you to focus on is, let us examine closely the corresponding max term and min term combinations. Can you see that this is a dual of this? What is a dual?
Yes, ma'am.
Complement. Complement, I told you. Yes. So if we apply De Morgan's law to this, will we get this?
Yes, ma'am.
Yes, ma'am.
What did the De Morgan's law say? It said replace each literal means each variable, with its complement. And so x, y, z are replaced by their complements and replace or by and. Yes or no?
Yes, ma'am.
Yes, ma'am.
And let us see whether the vice versa is true or not. So let us apply De Morgan's law to the min term now. So again, we see that when I apply the De Morgan's law here, what happens is I get x and is changed to or, y or z, which is this max term. Yes or no?
Yes, ma'am.
So the min terms and max terms are actually duals of each other. What are they? They are complements or duals of each other. Is this clear?
Yes, ma'am.
Okay, good. So, yes.
Ma'am, in this, ma'am, what is the row F says? Ma'am, it is written 0, 1, 0, 0.
So that is the output variable, no? That is the output variable.
Ma'am, how we will get that 0?
So, see, how we are getting that is immaterial here. Okay, why? Because f can be defined as any combination of these variables. That means, you know, any operation performed, f is, we assume that f is being defined as the result of any logical combination applied to these Boolean variables. And if you are talking about this output, then it might we might arrive at this output in many ways. That is not what is important here. So you can actually forget f for the time being. That is not what is important here. It is given to you only for completeness. There might be many ways in which I may apply logical operations and, or, and not to these three variables, and I may come at f, which gives me this output. Is this clear? For the time being, this is not relevant. Okay.
Okay, ma'am.
Now, the next thing is, like the midterms, we are first going to now talk about the product of sums form and then the product of max terms form. So you can see the expression written before you is what? It is the product of sums. This is one sum, another sum, another sum, ANDed with each other. Okay. Yes or no?
Yes,
Yes.
ma'am.
Yes,
So this
ma'am.
is the normal product of sum forms. When does it become the product of max terms form? It becomes the product of max terms form when I impose the restriction that every sum term must have all the literals present in the function. Okay, so if I write something like this, here I see each sum term is a complete max term. So obviously this can be called as a product of max terms form. Is this clear?
Yes,
Yes,
ma'am.
ma'am.
Is this clear?
Yes, ma'am.
Yes, ma'am.
Is there somebody who's saying no? You want me to repeat? Ask me a particular question that you, part of the concept that you want me to repeat. If you want me to repeat, please. Okay, I'll proceed then. So please see, let us look at the notation now. Now, for the product of sums form, the notation, the symbol which is used is a pi. Okay, pi, if you, as you might know from your previous mathematical knowledge, in any case is used to represent a product of numbers. Okay, so if I have a expression such as this, how will it be represented? It will be represented as product of, now this min term sometimes is represented as a capital M, somewhere it is represented as a small m. So you might have to see what your book or your question is saying and accordingly act. But here this denotes the min term. So min term, this is the product of the min terms 0, 1 and 2. What is the 0th min term? Please see from here. It is x or y or z. Okay, so in terms of ABC, if we are talking, it will be A or B or C. The first one is A or B or C dash. Yes or no?
Yes, ma'am.
And
Yes,
the
ma'am.
second one will be A or B dash or C.
C.
Yes? Any problem?
No, ma'am.
Okay, so now please see, let us look at what are these actually called. So these sum of product and the product of sum terms are together sometimes known as the standard forms. What are they called? They are called the
Standard forms.
standard forms. And the sum of minterms and product of maxterm forms are sometimes referred to as the canonical forms. Okay.
Yes, ma'am.
Now, please see that when we are applying any Boolean algebraic technique or even using the Carnot map, okay, to optimize a particular Boolean expression, what are we actually trying to do? We are trying to come from the canonical forms. We are trying to come from the canonical forms to the corresponding most reduced standard forms? Yes or no? Yes or no, students?
Yes,
Ma'am,
ma'am.
explain it once again, please.
Okay. So when I'm applying a Carnot map, for example, okay, what am I trying to do? What is the original expression? It is a form, it is in the form of the canonical forms. So either I'll start with a sum of min terms form or a product of max terms form. Okay. And what do I mean by optimally reducing that expression? What do I mean by that? We generally come down to what? We generally come down to a very small expression. Yes or no?
Yes, ma'am.
So
Yes, ma'am.
Yes, ma'am.
that expression is either in the SOP form or in the POS form. Okay. So using a Carnot map is actually a journey from the canonical form, from a given canonical form of expression to one of the standard forms. I can also put it like this. Okay, beta?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay, good. I'll again talk about this when we start solving the Carnot map. You can remind me when I take some example of how to use a Carnot map. You can remind me to talk about this again so that it is clearer. Now, please see what is an n variable K-map. So as we saw in the last class, what is an n variable K-map? A K-map for n Boolean variables contains 2 raised to the power of n squares, each representing a min term. Okay, initially we are talking about the SOP form. So in that case, each representing a min term. We will also see how to use a K-map to obtain a reduced POS expression. Okay, in that case, each square will represent a max term. Okay, but the most general definition of the K-map says that each square represent a min term, because generally we are working with the SOP forms. Okay, now we already talked about that why do we have 2 raised to the power of n squares? You remember that? Who will tell me? Why do we have 2 raised to the power of n squares in a variable, in a n variable K-map?
Ma'am, each min term has one box.
Ma'am, because there are 2 to the power n rows in a truth table, and Carnot map is a spatial representation of the truth table only. That's why.
Very good. So as we saw in the last class, we had seen that a Carnot map can actually be constructed from it is drawn out from a truth table. Yes. So let me just show you again. Can you see the new screen?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am. Yes, ma'am.
Okay, so this we said was a two variable Carnot map. We had seen that this was a two variable Carnot map. Okay, where you can see the corresponding minterms M0, M1, M2, M3. Okay, this I had discussed last time, and this is how we had seen a truth table, how a Carnot map pictorial is a pictorial representation of a truth table only. And that is why, since the truth table contains one row for every minterm, the Carnot map also contains one square for every minterms, resulting in a total of 2 raised to the power of n squares. Any problem up till now?
No,
No,
ma'am.
ma'am.
Okay, good. Now let us start with, first of all, how to represent a particular expression in a Carnot map. Okay, so what you see on your screen is the first example. So suppose I was to represent, the first question says, represent the Boolean function fab is equal to ab dash in a two variable Carnot map. So how to do that? So ab dash, they have taken, here I've taken, okay, let me just put it here. You've seen the question here? We are going to see how to represent terms on a K-map first, and then we will see how to solve a K-map. Okay. You can see the presentation now.
Yes, ma'am.
Yes, ma'am.
So every time you are required to draw a two variable Carnot map, you have to draw it like this. Okay. I had shown you this last time as well, if you remember. Today I'm going to take you over again. So let's say that I have a function f. Okay. It is a two Boolean variable function. Okay. And the first thing that I must represent is xy. Okay. So this is my Boolean expression that I have to represent. Okay. So how will I represent this? How will I represent this?
Excuse me, ma'am.
Yes.
Ma'am, in the second row it should be yes. That is what I was going to say.
Okay. Yeah. Thank you. But I just saw it.
So, ma'am.
Okay. Okay. Thank you, Beta. So please see. So suppose I had to represent this expression in the K-map, how to do it. So as we had seen earlier, this is 0, 0, 0, 0. Yes. When we
Yes.
are talking about SOP form, this is 0, 0, x dash y dash or x dash y dash. You remember all this or not?
Yes, ma'am.
Yes, ma'am.
Yes, and this is x dash y, which means 0, 1,
0, 1.
which means 1, right? Then x, y dash, which is 1, 0,
1, 0.
which means 2. And then finally 1, 1,
1,
x,
1.
y, or alternately 1, 1, which means 3.
3. 3.
Okay, which means 3. Okay, now what do I have to represent? I have to represent xy. Okay, so how will I represent? I will put a 1 here. I will put a, so I'll just put a 1 here. Visible to you? And in all other columns, I put a 0. In all other columns, I put a 0. Is this clear to everybody?
Yes, ma'am.
Yes, ma'am.
This is the simple representation of this expression xy. Okay. Now suppose I was to represent x dash y or xy. Okay. Then I would have put 1 here for x dash y, which is x dash y. This column, any problem? And the other one in xy. The other two squares are 0. Any problem?
No, ma'am.
No,
Is this
ma'am.
clear to everybody?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Now what will I do? So this is the same term, x dash y is this same term. Okay. And now the other one I have to put is in x dash y dash, which happens to be the first term. So I put it here. Any problem?
No, ma'am.
No, ma'am.
Good. Alternately, this could have been specified to me as sigma of m 0, comma 1. Okay. Okay or not?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Let me get the sigma symbol. Okay. Even if I got the same expression this way, I would have still written it this way. Or alternately, somebody could have written it like this. Is this okay?
Yes, ma'am.
All these expressions would mean the same. So you have to do this same thing to represent these terms on the two variable K map. Okay. Let us see how to represent terms on a three variable K map now. So now how many squares will I have?
8.
8.
Now, I think I have already shown you last time. I'll go over it again. I don't know whether you remember it or not. Okay, so when I have a three variable Carnot map, this is how it generally looks. Okay. This is the general representation of a Carnot map. This is the general layout of a three variable Carnot map. So what is the first term here? Please see, it is x dash, y dash, z dash, which is 0, 0, 0
0, 0,
is equal to
0,
0.
0.
Next is
0, 0, 1.
1.
x dash, y dash, z, which is 0, 0
1.
1.
is equal to
0.
0.
1. Okay. Then
Yes.
it is
1, 1.
0, 1,
0,
1, which
1,
is
1.
equal to 3. I told you to remember these.
3.
I told you to memorize these if you remember. 0, next is 0, 1, 0, which is equal to 2. Okay. Next, please see. Next
1,
is
1, 0, 0.
1, 0, 0,
0, 0.
which is equal to
4.
4. Next is 1, 0, 1, which is
1
equal to
5.
5. Next is 1, 1, 1, which is equal
7.
to
7.
7. Next is 1, 1, 0, which is equal to 6.
6.
Is this clear?
We need to memorize it.
Yes, ma'am.
Yes, I've always told you. These are the same terms that we use in the Boolean variables, in the truth table for three Boolean variables. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, if you remember. Yes or no?
Yes, ma'am.
Yes, ma'am.
Okay. So these are the same terms, please see. And how to remember it? Please remember, first of all, you must remember that these layout of the variables. So you must remember that, I'll just show you. Just give me a second, okay? Are you able to read these variables?
Yes, ma'am.
Yes, ma'am.
Okay, good. So, yeah. So you must remember that this will always be for a three Boolean variable x, y, z expression. This will always be x dash, x, Okay, the first column will always be y dash z dash. You have to remember all these. Okay, you have to remember all these. So the first column will be y dash z dash, the second will be y dash z, then yz, and then yz dash. Okay, you have to completely remember this K-map, the basic layout of a K-map. Similarly, for the two variable K-map, you have to remember it. Is this clear? Am I clear?
Yes, ma'am.
Yes, ma'am.
Okay, so how do I remember it? I always remember it as 0, 1, skip, 2, 3. Okay, 0, 1, skip, 2, 3, 4, 5, skip, 6, 7. Okay, now you will not face a problem. Once you remember their decimal numbers, then you will not face a problem. You will not draw the incorrect layout of the Carnot map initially. Okay. Okay, students?
Yes, ma'am.
Yes, ma'am.
Okay. Now let us see how to represent an expression in a three-variable Carnot map. So suppose I had this expression fxy is equal to x dash y dash z, or x dash y dash z dash, or x y dash z dash. Okay, suppose I have to represent this expression, then how will I represent? Then how will I represent? Okay, so let us, we can do it directly. That means we can, if we are given this form of expression, we could do it directly. We can just locate x dash and then yz in this row. This should be 1. Okay, then x dash y dash z dash. So x dash y dash z dash, this should be 1, and x y z, x y dash z dash, so this should be 1. Okay, all others will be, all other squares will be
0.
0. Okay, what will be the corresponding min terms for these? They will be
M0 plus
0,
M4 plus M3.
3, and 4. Yes or no?
Yes, ma'am.
Okay, so any way you see it, we are going to arrive at this final Carnot map representation. Is this clear?
Yes, ma'am.
Ma'am.
Any problem up till now?
No, ma'am.
Okay, so I'll stop here today, and next time we will first see what is the general layout of a 4-variable Carnot map and how to represent the expressions on that. And after that, we will look at a group of rules which we need to follow to solve a Carnot map. Solving a Carnot map means to use the Carnot map to arrive at a optimally reduced Boolean expression. Is this clear?
Yes, ma'am.
Yes, ma'am.
Okay, good, good. So what are you expected to do today? What is your task? So you are requested to please go over these uh, canonical forms and the standard forms. Okay, and remember, I am again saying, please see, I want you to remember all these combinations and their decimal equivalents. So for example, this is the 0, this is decimal 1, this is decimal 2, this is decimal 3. I've told you earlier also, if you memorize, these things will become faster. Okay, and eventually we use them so many times in architecture that it will help you if you can memorize these numbers. Okay, so 0 till 7, these are the 0 till 7, these are the 8 decimal numbers. Okay, similarly, for a 4 variable truth table, I have shown you the 4 variable truth table. It's been some classes now that I showed it to you, so you can refer to that recording, and you can go over a 4 variable truth table to also learn the corresponding binary combinations for uh, the first 15 decimal numbers. Okay, so they'll be 0000, 0001, 0010, 011, 0100, and so on and so forth. Okay, so you need to remember these. Okay, and then I want you to remember the basic layout of the Carnot maps. Okay, these two Carnot maps, because we are going to be solving our questions using these Carnot maps next time. Okay,
Yes, ma'am.
sit with a
Yes, ma'am.
paper and a pen next time. Okay, so that you can solve the Carnot maps with me. Okay. I'm going to be sharing the attendance link with you next. Please mark your attendance before you leave.